Good morning, dear students. In the last class, we had started discussing about the discretization process. We saw the types of elements to be used for discretization process. We also saw the effect of size of the element on the solution. Now we shall see the location of nodes. Location of nodes. We have a member here, a bar of uniform cross section with one end fixed. It is supporting a concentrated load. So what type of beam it is? It is a cantilever. When a beam of this type supports concentrated load as shown, one has to consider a node at the point where the concentrated load is acting. Sometimes several concentrated loads act on the beam. Then how do you consider the nodes? That also we see. For example, I have a cantilever like this. It is supporting two concentrated loads as shown. The loads are, say, P1 and P2. Then, where do you consider the nodes? One has to consider essentially the node where the load is acting. How many loads we have? Two loads. So therefore, I can have a node here at the point where the concentrated load P1 is acting. I can have another node here where the concentrated load P2 is acting. How many nodes we can consider here? Two nodes. One node here and another node here. Two nodes. Right? For example, I consider a couple. I take a cantilever like this. This is the cantilever. Now I consider a couple. If a couple is acting like this about an axis through the point shown, then where do you consider the nodes? The point through which the axis of the couple is acting. The point through which the axis is passing. Here you can consider a node. Right? How many cases we have seen here? Two cases. In the first case, we observe the concentrated loads acting. At the point of application of the load, you have to take a node essentially. In the second case, we have seen a couple acting clockwise like this, about an axis passing through this point. Therefore, at this point you have to consider a node. Right? Next one. This is a cantilever. It is supporting distributed load. From this section to this section, the load intensity is different. And from here to here, the load intensity is different. Here we observe two distributed loads with different load intensities. Two distributed loads with different load intensities. The load intensity of this distributed load is say Q1. The load intensity of this distributed load is a Q. Right? we don't have any concentrated load here. When you have a problem of this type, where do you consider the load? One has to consider the load essentially at the point where the load intensity is abruptly changing. This is the reason why I can mark a node here. At this point, the load intensity is abruptly changing. Right? Is abruptly changing. Now, we take an example and see how we locate the nodes. I take a cantilever like this. A cantilever. Here the beam has uniform cross section. One force is acting here at this point. Its load intensity is a P1. A couple is acting clockwise about this point. And distributed load is acting from this section to this section with the same intensity, say Q0. We have three types of loads. What are they? Uniformly distributed load, concentrated load P1 acting at this point, and a couple, say M0, acting clockwise about this point. Now, how many nodes you can consider here? Firstly, we say, because this is the point where the force is acting, where the concentrated force is acting, we can have a node here. We can have a node here. Because this is the couple acting about an axis passing through this point, we can have a node here. This is another node. So far, how many nodes we have? Two nodes. Right? Next. This is the distributed load. Its load intensity is same. Right? So therefore, you need not worry about this. We can have another problem. Again, I take a cantilever like this. I take a cantilever like this. Right? Now, I can have a triangular load as shown like this. This is the triangular load. The load intensity is linearly varying. The maximum load intensity is Q0. We can define here the load intensity as load per unit length. The maximum load intensity is Q0. What type of load we are having here? A triangular load. It is not uniformly distributed. Now, additionally, I have a force P here acting at this point. So now, I have a couple acting counterclockwise with magnitude M0 about this point. Now, how many nodes we can have? This is the point where the concentrated load P is acting, therefore we can have a node here. And this is the point through which the axis of the couple is passing, therefore we can have a node here. Two nodes we can have. Two nodes we can have. Okay? This is how one has to consider nodes at the point where concentrated load is acting, about the point the moment is acting, and at the point where the load intensity is abruptly changing. Now, third case, Observe here, we have a bar with abrupt change in cross section. Abrupt change in cross section. We have one and fixed. Where do you consider a node in this case? On the section where the cross section is abruptly changing. See here. This is a first part of the bar. First part of the bar. So this is part 1, we can say. Say part 1. This is second part of the bar. Say part 2. The cross section of the part 1 is same throughout its length. The cross section of the part 2 is same throughout its length. Where you see abrupt change in cross section, so here we can see the abrupt change in cross section, hence certainly you have to consider a node here. Certainly you have to consider a node here. Right? And another point is, if you observe this fixed support, so this is the rigid plane which may represent a wall. If you observe a wall, the area of this wall is bigger than that of the cross section of the part 1. So this part 1 is protruding from the plane of the wall. Therefore, we can see abrupt change in cross section. That is the reason why we can have a node here. We can have a node. Right? Now, part 2, if you see, we have a part with uniform cross section. Is there abrupt change in cross section? No. So what we can understand from this, one has to consider essentially a node where the cross section is changing abruptly. Right? So now, next one. This case, we have a bar made of 2 different materials. See here, this is steel and this is aluminum. 2 plates we have like this, one upon the other. Both are integrated with each other. They are integral parts. The properties of steel and aluminium are different. Along the length, the properties of steel are same everywhere. Along the length, the properties of aluminium are same everywhere. But if you take the cross section in the direction of thickness, the properties of this composite plate are changing at the interface. This is the interface where the properties change in transverse direction. That is the reason why you have to consider a node where the properties of the material change. This is the interface where the properties of the material change. That is the reason why you can take the nodes according to your requirement on this interface. That is what we have here. Consider the nodes on the line of discontinuity in the material properties. Okay. According to the requirement, you can have the nodes on this interface because the material properties change in the direction of thickness because we have a composite plate here. This is another consideration. Now we see. We have a wide plate with a socket at the end. We have a wide plate with a socket. You know how to make a socket. Take a plate made of, say, material wood. Take handsaw, then cut. You can make a cut to the required depth. Similarly, we have a plate here. The metal may be steel or copper or aluminum, doesn't matter. But a socket is given to certain depth. Right? This plate is loaded in tension. You can assume this socket as a discontinuity because the cross-sectional area of this plate from this end to this end is changing in the plane of socket abruptly. That is the reason why. Where there is discontinuity, we have to consider the nodes around the discontinuity as many as possible. Because stress concentrations occur in the neighborhood of the discontinuity. Around the discontinuity, stress concentrations occurs. Where the stress concentration is more in the vicinity of the discontinuity. Stress concentration is more. This is the vicinity of the discontinuity. Hence, the stress concentration is more. Therefore, we have to take the nodes as many as possible around the discontinuity when you solve a problem using finite element method. Right? Now, we take a problem and consider several forces. We also consider the abrupt change in cross section and see locating the nodes. Right? Now, what I do is I take a bar like this with abrupt change in cross section. Abrupt change in cross section. This bar has one end fixed. Now I consider distributed load, uniformly distributed load like this with load intensity say Q0, load per unit length. Now, the same bar is supporting a force P as shown. This is the point of application of the force. Now, the same bar is supporting another type of uniformly distributed load with different load intensity say Q0. The same member is supporting a couple in counterclockwise direction. The couple is acting about an axis through this point. M0 is the magnitude of the couple. Okay. Now, how you can locate nodes in this problem? When you want to solve this problem by finite element method, locating nodes is very, very important. How do you locate nodes? Now we take all the forces one by one. This is uniformly distributed load of intensity Q0. This is the uniformly distributed load of different load intensity capital Q0. The distributed load is abruptly changing. That is the reason why if you consider the section, here you can have a node, one node here. If you do not consider the node here, it leads to wrong solution. Be careful. Next one. This is the point where the force P is applied. Hence, you have to consider a node here. Now, recollect all the cases one by one. Next. At this section, cross-sectional area is abruptly changing. The cross-sectional area is abruptly changing. Therefore, you can consider a node here. Right? Now, the couple is acting about an axis through this point. Therefore, you can take a node here. Now, this bar is protruding outwards from the plane of the reservoir. Therefore, say here, the cross-sectional area is abruptly changing here. Hence, you can consider a node here. Okay. Now, is there any possibility to add few more nodes? No. So, how many nodes we have? 1, 2, 3, 4, 5 nodes. This is node 1, node 2, node 3, node 4 and node 5. You cannot have the nodes less than 5. If you want, you can have few more nodes. But when you increase the number of nodes, the computation time also increases. That is the problem. So try to take fewer elements and solve it in lesser time. Otherwise, it takes more time to compute. Okay? Now, I take another problem like this. I take a composite plate. This is the composite plate. The plate is made of two different materials. Now, it is supporting a force like this P as shown. This is the point of application of the force. The plate is supporting uniformly distributed force like this. The load intensity is Q0. Now, say here, a triangular load is also acting with a different load intensity like this. The maximum load intensity of this triangular load is, say, capital Q0. Now, how do you locate nodes? That is the question. This is the point where the load intensity is abruptly changing, therefore I can consider a node here on the beam section. Right? Next. This is the point where the force P is acting vertically downwards. I can have a node here. Second node. Now, this is the section where the cross-sectional area is abruptly reduced, therefore I can have a node here. Now, have I correctly located the nodes? That is the question. Because here, the plate is made of two integral parts. The materials are different. That is the reason why this is not the correct location. I can have a node here. This is a composite plate, therefore this is not the correct location. I can have a node here. This is not the correct location. I can have a node here. So how many nodes here? 3 nodes. Why I can have a node here? Because this is one material and this is another material. The material properties are different in transverse direction. This is a line of discontinuity, or you can say the interface. That is the reason why you have to consider the nodes essentially on this line of interface. Right? Therefore, how many nodes we have? 3 nodes here. 3 nodes. This is how one has to consider the nodes essentially. So, location of nodes is very, very important. Okay, now simplifications afforded by the physical configurations of the body. Observe here. Sometimes we can simplify the given problem. Now, how do you simplify? Let us see. This is a plate with central hole. A hole is drilled with certain diameter at the center of the plate. The plate is loaded in tension. Therefore, sigma is the normal stress. Now, if you observe carefully, under the action of the pull, every point on this plate displaces in the direction of loading. In the direction of loading. Take a rubber band. Take marker. Mark a point on the rubber band and apply pull on the rubber band. Then this point displaces in the direction of force applied. But the point does not displace in a direction perpendicular to the direction of force. Similarly here, this point can displace in the direction of force applied, but this point cannot displace in this direction. This point cannot displace in a direction perpendicular to the direction of force. This point can displace in the direction of the force. In the direction of the force. That is the reason why, instead of taking the entire plate, if you take half the plate as shown, see here, right? These points cannot displace in a direction perpendicular to the direction of loading. Every point on this line moves in the direction of loading. That is the reason why you can have the nodes on this face and similarly on this face, on both sides of the hole as shown. One may consider half of the body if the loading conditions and the geometry of the body are symmetric. This plate has a vertical line of symmetry, therefore you can take half the plate. Right? And loading is also symmetric about the horizontal axis. That is the reason why, instead of taking entire plate, half the plate as shown you can take and solve the problem by finite element method. So instead of taking the entire domain, if you take half the domain, the number of finite elements decreases. Therefore, the computation time also decreases. And you can get the solution at faster rate. Right? Now, finite representation of infinite bodies. Observe here. This is a body. Its length is very large. Right? The cross-sectional area is same throughout its length. Assume that the transverse force is acting on the other side. You can assume a water reservoir. If we observe the structure of the dam, on one side, the water pressure acts on the dam. What type of loading it is? Transverse loading. We observe a dam like this. Then water pressure acts like this. What type of loading it is? It is the transverse loading to the dam. Have you seen the dam? Its length is very large. What type of loading? We observe transverse loading. So therefore, instead of taking the entire dam, if you take a unit slice as shown, slice? We cut the bread into slices, into pieces. Take a bread, we go to the market and buy the bread. the bread is in the form of a rectangular prism. When you cut it, each slice, appears with same shape. The cross section of the slice is same. Right? Similarly here, instead of taking the entire dam, if you take a unit slice and consider, the strain in the direction of the length is 0. The strain in the direction of length equals to 0. Therefore, you can consider it as a plane strain case. Instead of taking entire domain, if you take a unit slice and consider the action of the water pressure and solve it, the solution of this is the solution of the entire problem. Right? See how faster you get the solution when you take the whole domain and discretize into finite elements. You solve the problem. It takes more time to give the solution. Instead of taking the whole domain, if you take a unit slice and solve the problem. As plane strain case, you get the solution in lesser time. Okay? Here students, now we shall see node numbering scheme. When we solve the problems of elasticity, all the equations appear in the form of matrix, in which most of the matrices involved are banded. Hence, the computers require less storage to store the elements. You need not store all elements of the matrix. When we solve a problem by finite element method, all the equations appear in the matrix form. In most of the problems, all the matrices are banded. Therefore, you need not store all the elements of the matrix in the computer, because the matrices are banded. The bandwidth depends on the node numbering scheme and the degrees of freedom of the node. If you take one-dimensional problem, for example, such as an axially loaded bar, what type of element we choose here? One-dimensional element. It connects two nodes. That is the reason why at each node, if you observe, each node has only 1 degree of freedom. This is node 1, this is node 2. Node 1, node 2. At each node we observe same number of degrees of freedom. This domain, if you discretize into two subdomains, how many nodes we consider? One node here, second node here, third node here. This is first node, second node, third node. Node 1, node 2, node 3. At each node we observe only 1 degree of freedom, because it is a one-dimensional problem, axially loaded bar. And this is the node numbering. How the nodes are numbered? 1, 2, 3. This phenomenon you can say node numbering scheme. The bandwidth of the matrix depends on the node numbering scheme and the degrees of freedom at each node. But the degrees of freedom at each node do not change. That is the problem. So what is there in your hands? The node numbering scheme. How you number the nodes? That is very, very important. Numbering should be done to all the nodes carefully. Degrees of freedom per node do not change. It is not in your hands. What is there in your hands? Node numbering scheme. You have to number all the nodes carefully. If you want to minimize the bandwidth of the matrix, the storage requirements and solution time also decrease. If you minimize the bandwidth of the matrix, the storage requirements of the computer and the solution time also decrease. Understand? When the bandwidth decreases, the storage requirements of the computer also decrease. The solution time also decreases. Because the number of degrees of freedom at each node is fixed, the bandwidth can be minimized using node numbering scheme. Right? Now, how we determine the bandwidth? See, this is a huge structure which has how many stories? 20 stories. Right? This is node 1. You can assume a structure like this with 20 stories. So this is first node. This is second node. This is third node. This is fourth. This is fifth. This is sixth. This is seventh. This is how I give node numbering. Assume that at each node there are 3 degrees of freedom. Okay. How many nodes I have? 84 nodes. That is the reason why. How many degrees of freedom I have? 84 into 3. That is what I can have. 84 into 3. 252 degrees of freedom I can observe in the structure. Right? So now, if you want to write a overall stiffness matrix for this structure, what is the size of the overall stiffness matrix for this structure? The overall size of the stiffness matrix of the structure is simply 252 by 252. That is what we can understand. How we get this? We understand, in the days to come. Right? The size of the overall stiffness matrix, or you can say global stiffness matrix, is 252 by 252. 252 by 252. Very big matrix you get. Very big matrix you get. If you prepare the global stiffness matrix, the stiffness matrix for the entire structure, the size of the matrix is 252 by 252. How many rows are there? 252 rows. How many columns are there? 252 columns. Very big matrix. The matrices with this much size you cannot operate by hand calculations. You have to depend on computers. Right? And the bandwidth of such matrix is 15. Therefore, the storage requirements for the upper bandwidth is 15 into 252. How many locations? 3,780 locations. You want the storage requirements to store the data. How many locations? 3,780 locations. Instead of storing all the elements of the matrix having the size 252 by 252, you can store the elements at how many locations? 3,780 locations. This is the advantage of half bandwidth. Right? Now, how you determine the bandwidth? The formula for determining the bandwidth is maximum difference between the number of degrees of freedom at the ends of any member plus 1. This is the formula. Maximum difference between the number of degrees of freedom at the ends of any member plus 1. How you write? Bandwidth B equals to D plus 1 into F, where D is the maximum difference between node numbers for all the elements and F is the degrees of freedom at each node. If you remember this formula, you can determine the bandwidth. Dear students, what we have learned today? So we have seen locating the nodes when a structural member carries several nodes. We have seen locating the nodes when the cross-section area is abruptly changing. We have seen locating the nodes when the material properties are changing. We have seen locating the nodes when there is discontinuity, right? And we also have seen the bandwidth of the matrix. Thank you very much.